Avatar. Thank you for inviting me. So in this talk, I will. So that's the title: Overparametrized Neural Network and Generalization Bounds. I will speak about a joint work that we published recently in MediaTek Research. So first of all, so the aims of this talk, I will explain what are overparametrized neural networks, what is the overparameterized regime, neural tangent kernel, and the associated buzzwords. So as you can see in point one, I mean, basically, I will make sense of the statement as number of parameters in neural network goes to infinity. Training behavior of the neural network will resemble a kernel method, so a linear method. So this is the overparametrized regime, but of course this needs to be made precise, and I will aim to make this more precise in this talk. After that, I will pass to the second part, which is I would like to show how in this overparametrized regime to derive error bounds for the neural networks. So there were quite a few works on that, and we derive error bounds in a certain way in our paper, which is listed here, uniform generalization bounds for overparametrized neural networks. And I would like to explain, I mean, what do we do, state the theorem, and the methods that we use. Just putting it here, fully connected neural network formula. So I will talk about, without mentioning in the future, I will talk about these fully connected neural networks where the activations of the previous layer are so this is a transition between one layer to another. So ZJRD is the output of the previous layer, and L+1 is the next, and ZL+1 are the next layer. And we're just basically, so this is the regular neural network. We're just multiplying by, so we're making an affine transformation of the previous activations. But what is important here, so sigma is will be a ReLU activation, ReLU to the power of s, some nonlinearity. And what is important here is the normalization, because so we will divide, so we will somehow initialize initially the parameters wi and bi, but then we normalize the parameters of the neural network, the multiplicative parameters of the neural network. We multiply them by square root of the width of the neural network. So this is the normalization that will make the regime, the overparametrized regime, happen. Sorry? Any questions? Okay. So the first thing that I want to do before stating the results and explaining what is overparametrized regime, I need to give a brief overview of what are kernels and what is a kernel method. So basically, kernels are kernel functions are so kernel functions are generalizations of positive definite symmetric matrices. So a kernel on a domain D will be, well, in our case, it will be a continuous function. So D, and it will be a continuous function from D cross D to R that is symmetric, and positive semi-definite. So this is what semi-positive definite means. It's basically the same as for positive semi-definite matrices. So the quadratic form that is derived by this by the matrix is positive definite. This is what this equality means here. And for each kernel, we have an associated what's called RKHS, reproducing kernel Hilbert space. And this is so this is the space, well, infinite dimension, just a vector space in infinite. So this is a Hilbert space, can be infinite dimensional in general. And if you, so the way that it is built is by looking at functions of the type. So you look at the kernel, you fix a point xi, and this is so this is a function of d, right? This is a function defined on d. The dot is your variable, xi is fixed, and then you look at linear combinations of such functions. So xi are some points in d, alpha is some points in r. You look at finite linear combinations of such functions, and then this forms a linear space, and then you take the closure of this linear space. Once I have to, and once I'm saying closure, I have to say in which metric you take limits. So so this is a Hilbert space, and the inner product of this Hilbert space is exactly the inner product defined by the kernel. So we know that in finite dimensions, a positive definite matrix is exactly, you can all in a finite linear space, all inner products are actually bilinear forms defined by a positive definite matrix. And here it's exactly the same thing. When we look at finite linear combinations of functions of that sort, so their inner product is simply defined by the kernel, so by the inner product, so by this formula that I write here, down here. And inner product always defines a metric, a norm, and it's with respect to this norm that we look at the closure of the Hilbert space, would form the Hilbert space. So when we're talking about kernel methods will seek, so from now on H will be, there will be a kernel, and H will be the associated reproducing kernel Hilbert space. And kernel methods seek predictors. So given training data, they will seek predictors in the associated Hilbert space. So basically, what you have to think about is given training data, xn and yn, we will have the predictors are of the form. So we look at linear combinations. So this is a function of x. We will look at linear combinations of functions of the form. So these xi's are chosen with respect to the data. So this is the same points as the data. And basically the way that you should think about this type of predictors, so those are finite linear combinations of this type. And the way you should think about them is, so the kernel, for a new data point x, the kernel specifies how much correlation do you have with the data that you already know. So how close is x to the xi's? Either it's negatively correlated or positively correlated, and so on. And then you look at the predictors are linear forms of these, linear combinations of these correlations. So alpha, the coefficients alpha I here are chosen to minimize a loss objective with respect to the data. And so they're found either by optimization or just by, so these are linear methods, so by inversion. So for example, if you have the regular mean squared loss with the regularization, so you look at, so you're depending on the data, your loss with respect to the function f, h, is basically given by this formula, plus regularization. It means that, so the norm of the, so you penalize the norm, the RKHS norm of the function h. So this type of loss is uniquely minimized by predictor that is listed here. So this is the same in as ridge regression. So this is called kernel ridge regression, and this is an analog of regular linear ridge regression. Any questions so far? Okay. So as I said previously, alternatively, loss objectives can be minimized by gradient descent, and somehow if you look, you can look, I write here a functional gradient descent because you can actually optimize this gradient descent in the space of functions. So it's a bit of a different way to look at the gradient descent. So this differential equation is analog of all differential equation that you know for the parameters of a neural network. So basically you optimize the parameters in the direction of the gradient of the loss function. Only now your parameters are functions in the RKHS. So so this is what is so you optimize. So you optimize these functions, but there is no problem. So there are technicalities involved by functional gradient descent. Is just based on the fact that you can define derivatives of mappings between any two normed linear spaces. And in this case, the mappings are so one linear space is the RKHS, and the other linear space is just R, the real line, where you have the loss is on the real line. So it's basically the same thing as optimizing parameters of a neural network. It's the same equation, only now f is a function in the RKHS. So I would like to say that the gradient, the functional gradient for a mean square loss, continuing the example from before, is this kind of function. So this is the gradient. So the gradient at a point f is of this form. So you look at the derivative. So this is the regular derivative of the loss, fxi minus yi, and you multiply this loss by the. So this is so the differential itself is a function at a point is a function on the RKHS. So the overparametrized regime is when happens exactly when the neural network gradient descent can be approximated by this type of kernel gradient descent with and the kernel being a very specific kernel, which arises from neural network and is called the Neural Tangent Kernel.
Hello, may I ask a question?
Yes.
I'm just curious about the notation here. So can you define what is the domain and the values of f? Because it might be very confusing because if we interpret f as like a real valued function, then partial f over partial t should be some kind of like a scalar, but it seems not. So I just want to clarify what is the definition of f.
Okay, so f is a function in a Hilbert space, and so I didn't say before that. So what we the values of the functions are in R. We're talking about. So the value of the function is in R, while the domain of the function is in D. So the whole kernel is defined on the domain D and therefore the value of the and the functions in the associated Hilbert space are from the domain D to R. Now the confusion here. So this is not a regular gradient. So this is not a scalar. So this is not a regular gradient in the sense that, so you can define a gradient between, you can define a derivative between any two mappings from one linear space to the other linear space. In the case of, in general, one second. So I don't have a pen with me, but the derivative. So if you look at the derivative of a function at a point at a certain point, this is a linear transformation. Is that so the gradient itself can be thought of, at every point it's a vector, but a vector defines a linear transformation, which is a linear approximation to the function, right? So if we look at the function, so what we're supposed to get here is a function f at a point t plus h minus a function f at a point t equals its gradient at the point t times h. And when you so this is the definition of the derivative. So the functional derivative here is doing exactly the same. It's a linear approximation. Only now it will approximate something different. So it will approximate. So if we look at the derivative of f with respect to t, then this gradient is supposed to be a linear approximation of, if you look at, so f at a point t plus h is one function, minus f at a point t is another function. Those are two functions in a Hilbert space, right? And what the derivative should do is give a linear approximation to these two functions. I'm not sure if I'm explaining myself well, but this basically drives. So this differential equation will draw a curve in the Hilbert space of functions.
Okay, I see. So each f of t is like a point in that Hilbert space.
Exactly.
And that derivative means that a linear approximate, like that partial derivative times the delta t is an approximation of f at t plus delta t minus f at t, I guess. Okay, so both sides are like. So
it will say that f at the point t plus h minus f at the point t equals to this derivative. So actually it will be okay, so this is a functional derivative. So this derivative can be defines a functional in the Hilbert space. So this is actually a function. What we look at here, it's a function itself. The derivative itself will be a function in the Hilbert space. And a function in the Hilbert, so any function in a Hilbert space defines a functional, but taking this function and looking at the inner product of this function with any other point in the Hilbert space. Does that? So this is the kind of so this is what will be. But this is really this is a technical detail, and it's not. I didn't want to derive it here, but so the value of this derivative itself is actually a function itself in the Hilbert space, and you can see it here. So what I write here is a function in the Hilbert space, and that's because of kxi, the dot here.
I see.
Okay, so this is a function, but any function defines a functional in the Hilbert space, and this function will be the linear approximation to. So this differential equation is an evolution of the law will be evolution of the parameters of the function or of the function in the Hilbert space. Okay, it will draw a curve in the Hilbert space. We will look. The same can happen with so you can do exactly the same analog with the neural network. So instead of looking at the parameters of the neural network, you can look at f shall be its output, the output of the neural network. And you can look at how the output changes. So I should add here a point x, how an output of the neural network changes at the point x. And you will have here, you can, and you can draw analogs between the two. So instead of looking at the parameters, you look at the function, at the output of the neural network, at the function of the neural network itself.
Okay, I guess I understand your formulation now. Okay, that works. Okay.
Okay. So, so as I said, the overparametrized regime is exactly when neural network gradient descent can be approximated by kernel gradient descent. So I should explain. How this happens. So now we're looking, let F be an L-layered, fully connected neural network with the transitions that I pointed out earlier. Theta are the parameters of the neural network, and usually these are random parameters because we initialize theta randomly at time 0. And theta t, we will denote these random parameters, the change in the parameters, or the parameters after performing t steps of gradient descent flow. So flow of this form, just instead of f, look at the this is a f will be changed by the parameters of the neural network. So now I'm defining what is the neural tangent kernel. A neural tangent kernel is just the derivative. So the neural tangent kernel at xy is just the derivative of the neural network at the point x times the derivative of the neural network at the point y. So you should think, so this is the partial derivative with respect to the parameters, and you should think about it. This is a big vector of this is a big vector depending which depends on the point x, and it's multiplied by the same vector but at the point y. This is the neural tangent kernel. This is just a definition for now, and this actually defines a kernel, a positive definite symmetric function, as I said before. On here it's on the domain that the neural network is defined, so where the neural network takes values. Sorry, where your data sits. So here is the theorem. So in general, this kernel is a random kernel, and it depends on parameters theta, and so it will depend on time t. It will change during training. This kernel will change all the time. So so this kernel is basically what I'm trying to say is this kernel is random and it changes with t during training. But now here is the theorem in that makes the overparametrized regime work. So as the width of the neural, so N1 and NL will denote here the width of the neural network. I haven't written it down, but I should. So N1 is the width of the first layer, and L is the width of the last layer. We always assume here that the output of the neural network is in R, so it's just a scalar. And the input of the neural network is not among these dimensions. The dimension of the input is fixed. So this is the width of the hidden layers of the neural network. So as we send these widths to infinity, and if we initialize the initial parameters of the neural network by a standard Gaussian, remember that the parameters of the neural network, so the neural network in our case has a very specific normalization to these parameters. We normalize the multiplicative parameters by the width of the neural network. So as we send the width of the neural network to infinity, the normalization also changes. So in this case, as we send the width to infinity, the neural tangent kernel that I defined now here, which is the derivatives that I defined here, tends to a kernel. So this is the theta xy is a certain kernel which becomes non-stochastic. So I will write here the equation of, I'm writing here the equation of theta xy, but what is important is that theta xy is a deterministic kernel and it does not depend on t anymore. So this is the theorem proved in a seminal paper about neural tangent kernels when they were first introduced. Somehow this theorem is not hard to prove when at theta 0. So when you just initialize the parameters as the width grows to infinity, the fact that the kernel goes to something which is non-stochastic, so at t0 I do not need to prove it for all t, I just need to prove that this kernel grows to something deterministic. This is a result of a law of large numbers based on the normalization, so somehow the 1 over square root of n. So you can see you will have a normalization here. This is a multiplication, so you'll have normalization of one side of 1 over square root of n, on the other side of 1 over square root of n, square root of n being the width of the neural network. And as NL grows to infinity, and so the multiplication will give you just a division by 1 over square root of n, NL, NL being the width of the neural network, and sorry, without the square root, 1 over NL. And this will use, so this multiplication is sum of many coordinates. So you multiply the first coordinate, and then you sum the multiplication with the other, so on and on. And what you will have here is an empirical average. And in fact, and by the law of large numbers, when n will tend to infinity, when the width will tend to infinity, you will converge to something which is deterministic. This is how this theorem works. So, but this is at time 0. And proving it for all times t, which during the training is highly is the non-trivial part, is the hard part of the theorem. So this convergence actually happens at all times t, as I said. The limit being an expectation. So the limit depends on the activations of the neural network, and so there is. There are assumptions here. So for example, one of the assumptions is that the activations are twice Lipschitz differentiable. But what you have to, I do not want to go into technical details, but what you have to think about is that these assumptions work, for example, for the mean squared loss that I told you about earlier. So the definition of the, so kernel, I also do not want to, I don't think that it will make much difference for me to say how it's exactly structured. What is important is it will be an expectation, and it will be an expectation of a Gaussian. It will in a few slides we will see what is a Gaussian process. So it will be an expectation of a Gaussian, and the correlation of the Gaussians will be determined by the points x and y. But what is important is that this kernel, limiting kernel, will depend on the activations sigma. Okay, any questions so far about the theorem? I haven't said what are the implications of the theorem. So right now, all you have to think about is that we have this kernel, which is based on the derivatives of the neural network. This kernel changes with the training of the neural network, but in the infinite limit, as the width of the neural network tends to infinity, this kernel tends to something which is deterministic and does not depend on t.
Okay, I have some questions regarding to the theorem. Okay, so first of all, what do you mean by n1 to nl goes to infinity sequentially?
So that's what I said in the, so, okay, so this is a, so this is a technical thing, but so the way that so in general, you look at the width of the neural network, and you can send the width of the neural network to infinity. They can grow to infinity in various ways, right? It's a vector, so you can, for example, send the last one to infinity and make the last one big, or make the last one be 5 times the previous one, and then the previous one will be 5 times the before the previous one, and so on and on. There are many modes such that all the layers can go to infinity. So so basically the theorem here is that this will be true in the limit. This will be true once. So this will be an iterative limit. So first of all, you send n1 to infinity, then you send n2 to infinity, then you send n3 to the third layer to infinity, and so on and on. And then basically, so this is the way that this is the right arrow here. The kernel. So if you would have sent them in different order to infinity, this result is no longer true. Does that answer the question?
So you mean you first send n1 to infinity, then you send n2 to infinity, and so on?
Exactly. So you look at an iterative limit. So you look at, yeah.
Okay. And the second part is that what do you mean by uniformly in T? And is it does it converge like in the strong sense or in the weak sense?
So it will converge in probability. So the convergence here is in probability. And what I mean by uniformly in T is that the difference, the supremum over all T of the difference between these two quantities goes to 0 in probability.
Okay,
so that's the uniformity. Okay, so for all T simultaneously, kind of.
Okay, do they make any assumptions on the the activation functions? If the activation function in a sense explodes when yeah, I'm just wondering, is there any additional assumptions?
Twice differentiable, and just a second. So what I remember, so there is an assumption. What I remember is maybe not twice differentiable. So once differentiable, and the differential is Lipschitz continuous, something like that. And the differential is Lipschitz. The derivative is Lipschitz.
Okay, I see.
So there will be, maybe I'm mistaken a bit in the assumption, so it will be twice differentiable, but I think it's once differentiable and the derivative is Lipschitz continuous. So almost twice differentiable, right? So if a function is Lipschitz continuous, then it's differentiable almost everywhere. So it will be almost twice differentiable. Okay.
I see. So does that include the commonly the well-known ReLU function?
This includes this will include. So this theorem is valid for the ReLU function. So there will be so the ReLU. You're right. I mean the ReLU function is not even once continuously differentiable, but I think that almost everywhere will be enough. So so as I said, now I'm definitely mistaken in the assumptions of Lipschitzianity. It's probably almost everywhere. I do not remember. Sorry for that. But it is true for the ReLU function. This I can guarantee.
Okay, thank you. No, yeah, okay, no further questions for me.
Okay. So, so what does this mean? So training a neural network. So training a neural network in function space, you can write the same differential equation as the one for kernel methods. So here, what I wrote here, f was a function in the Hilbert space, and I said that this is differential equation that shows an evolution of functions in a Hilbert space. But actually, you can look at this differential equation and not look at, typically, we would look at this differential equation and and instead of f, we'll have the parameters of the neural network. But we can actually look at the output function of the neural network as well, instead of the parameters. And if you look at these and if you look at the output of the neural network, instead of just looking at the parameters with the same differential equation, you will see that the evolution, the evolution of the neural network will define, so for mean squared loss, you will have the same equation as in as written here, with the kernel here replaced by the neural tangent kernel that I defined in the next page. But the neural tangent kernel here will be, as I said before, stochastic and in general dependent on t. So now the limit theorem says, the limit theorem that I showed you actually says that as the width grows to infinity, this kernel becomes similar to what is written here. So it becomes non-stochastic and non-dependent on t. And so you will have the same thing. And basically what and the implication of the theorem from the previous page that I showed you is that training in the overparametrized regime, so as the widths of the neural network grow to infinity, the output of the neural network, the functions themselves, can be approximated by kernel gradient descent, where the kernel is this limiting kernel, this limiting kernel that is the limit of the neural tangent kernels. So this is the implication of the previous theorem. And this is what point 2 says. So this is called, this type of training is called the lazy training regime. And the reason is, so as I said before, the kernel methods are linear methods. And it basically, so one way to look at it is that the approximation, so f is the output of the neural network. And here I'm writing omega are its parameters. Sorry, it was supposed to be theta. This is a typo, but omega is theta. So omega are the parameters of the neural network. And what I'm writing here is that the first order Taylor approximation is valid for the neural network throughout the whole training. We know the Taylor approximation is valid only when the initial parameter, so the parameters at time t, differ from the parameters at the time 0 by only a small amount. This is when Taylor's approximation works. But in fact, what I'm saying here is that throughout the whole training, this approximation will work. This is somehow implicit in the previous theorems. And the reason is that actually the parameters, and it was one of the observations according to which the whole theory of the NTK was developed, the parameters of the neural network, of these highly overparameterized neural network, do not change a lot during training. So one of the observed phenomena was that if you have a very wide neural network, after training, its parameters are very close to the initial parameters of the neural network. And this is And this is the phenomenon that we are observing here. That's why it's called lazy training regime. You do not change the parameters by a lot, but actually a small change in these parameters allows for a very big change in the output, in the function, in the predictor itself. But the reason is, of course, that the number of parameters is very, very big. So cumulative effect of changing each parameter by a very small amount results in a big change in the functional space. So, so this is the NTK regime. Any questions concerning that? Yes.
I have a question. So here you mentioned about here you use like a Taylor series expansion to the first order, and as you mentioned, it has an assumption that the omega of t should be close to omega of 0. But then in the next bullet you mentioned that just a small change in the parameters will result in a huge change in the output. So I'm wondering if that is the case. Does that mean that the second order and higher order term will come into place even when the difference between omega of t and omega of 0 is just adequate amount?
Sorry, can you repeat the last sentence? What about the adequate amounts?
I mean, if you mentioned that just a small change in the parameters will allow for a big change in output, does that mean that even a small amount of change in the omega of t, apart from omega of 0, will result in like the higher order term to come out? So you need to take that into account to consider that kind of Taylor series expansion.
So what will be, so the fact that there will be a change, a large change in outputs is that, okay, we train the neural network. So at time 0, it will spit something completely random, while at time t, it will be a trained neural network. So it will, so actually you can observe that the output of the neural network will correspond to the data, and there will be, in the outputs, there will be significant change. The change in the parameters will be small. So the thing here is that the fact that the change of parameters is small is basically the main thing that they prove in the theorem. So in order to prove here this convergence, the convergence for all t is exactly what you have to do. What you have to do is to show that this convergence at time 0, which I said is easy. But then, in order to generalize it for all t, the next step will be to prove that as the number of parameters grows to infinity, the variation among the parameters during training does not change, has very small change. So this is kind of the so this is kind of the feature of the proof, and the thing is that the Taylor's approximation is good when the change in parameters is small, and also the error term, which is basically the error term is based on the second derivative, is based on the Hessian, is small, of course. So that's the main. So that's the main thing which I didn't say here when the Taylor approximation is good. So what I can say that technically, the normalization that I mentioned to the activations. So we normalize the activations by 1 over square root of the width of the neural network is exactly the normalization that allows the Hessian matrix to have bounded eigenvalues for the Taylor expansion to have small errors. So yeah, so it's not only that so this normalization does not only show that this difference is small, the difference between the parameters is small, it shows that the variation in the parameters is small compared to the second derivative. So these are kind of features of the proof, and going deeper into into the theory. Also, this lazy training regime has nothing explicit to do with a neural network. So in fact, there is a paper that shows how this lazy training regime also exists in other methods where you can over-parameterize. So you have predictors, you have families of predictors, and you somehow take the number of parameters to infinity in a certain way. And there it also depends, very heavily depends on the normalization, how you normalize these parameters. And it's based on the analysis of this of the errors in this linear approximation. Does that answer the question?
Okay, yes, it answers the question. So mainly you mentioned that the Hessian is actually some kind of like a bounded, and if the change in omega is small, then exactly the second the higher order term should vanish. It should be negligible. Yes. Okay, I understand.
So it's exactly what you have to prove. So the Hessian will be small compared to the variation in the parameters, because the error term here will depend on WT minus W0, omega t minus omega 0 to the power of 2. So this is the variation in the parameters times the Hessian matrix. So the product must be small. That's what you have to. That's what you have to prove.
May I add a point here?
Yeah.
So the paper, I shared the paper in the chat. I think everyone can see. So in this paper, they actually prove a bound on the second term, which, as Michael said, is the difference in the parameters multiplied by Hessian multiplied by the difference in parameter, basically a quadratic form of the difference in the parameters from the initialization with the Hessian matrix. So this paper proves bounds on the spectrum norm of the Hessian matrix. And their final result is that the second term grows, scales with 1 over square root m, where m is the width of the network. So they basically show that when m goes to infinity, the second term goes to 0 in order of 1 over square root m.
Thanks, Atar. Basically to say that, so this type of normalization of the weights by 1 over square root of n sends in the overparameterized regime, sends the dynamics of training of the neural network to the simplest dynamics that there are, which is linear dynamics. This is what happens here. So there are other regimes. So if you would normalize by something of different order, you will get non-trivial dynamics. And this is, I think, has to do with mean field theory, which I don't know anything about, and I hope to know about it soon. But I do know that this is the regime that is depicted in the mean field theory, where the normalization is basically different. So I want to stress this fact that it's basically everything here depends on picking your normalization correctly to the weights of the neural network. And this sends the training regime of the neural network to the most trivial training that actually exists. I must also say that this type of this overparameterization setting is it's very nice in the sense that it allowed some insights into the theory of neural networks, because as we know, training dynamics of finite neural networks are very complicated to understand. So it gave many insights, but empirical results show that actually neural networks perform well, not in the overparameterized regime. So this is also kind of a caveat to the whole thing. Okay, so now I want to pass to the second part. I do not have a lot of time, but I hope to just at least say the results. There is so this is the derivation of error bounds. So now in this overparameterized regime, we know that in overparameterized regime, the neural network the training dynamics of the neural network are approximated by training dynamics of a kernel method. And we know how to derive errors for the for kernel methods. I will tell here to you about one approach of how to derive errors for kernel methods. But all of these methods in the end depend on knowledge of the spectrum of the kernel, or a kernel. So a kernel is a positive definite operator, or let's think about a positive definite matrix. A positive definite matrix, a symmetric positive definite matrix, is diagonalizable. That we know from linear algebra. And this is true also for a kernel. And so we can derive error bounds for kernel methods, and this has been known for some time, based on the knowledge of this on the knowledge of the spectrum of this kernel. So what we do is so in our work, in order to derive these error bounds, we analyze the spectrum of the specific kernel at hand, the neural tangent kernel, and basically understand the decay rates of decay of its eigenvalues. And I'd like to explain as much as I can from it, but this is kind of a taste because I'm not sure if I'll have enough time. So my first slide here is to say that there is an intimate connection between a kernel methods and Gaussian process. Gaussian process is a process. It's a random family of functions defined on a domain D, and if such that, so if you look at the finite dimensional distribution, so if you look at these vectors, you fix points x1 at xn, the distribution of the points fx1 to the fxn will be Gaussian, is always Gaussian. Any Gaussian process defines a kernel naturally by just looking at the covariance between fx and fy. So this is the definition of, so the kernel at the point x and y is basically the covariance between the Gaussian process at the point x and the Gaussian process at the point y. Remember, Gaussian processes are random functions. So on the other hand, but this is a much deeper result, kernel together with a mean function define a Gaussian process. This should not surprise you too much, because actually a Gaussian distribution, what is enough in order to define a Gaussian distribution? So give me its variance and give me the expectation of the Gaussian distribution, and this defines the Gaussian distribution. So here it's the same thing, the variance covariance matrix, or the kernel, and the expected mean define a GP. So there is a strong correspondence between kernels and GP methods, and actually Gaussian process methods. And actually this correspondence goes to, so I have to explain what is Gaussian process regression. So Gaussian process regression is assume there is, we observe a function of the form. So we observe random data, and it's of the form f, where f is a Gaussian process. At the point x, it's a Gaussian process, plus some independent noise. So Gaussian process regression is basically, so this is our model, and Gaussian process regression is basically, once we have obtained observations, we observe data, we condition our Gaussian process on this trained data, and we get a posterior. This is Bayesian approximate inference. We get a posterior, and what is important is in this posterior distribution, so after observing the data, is again a Gaussian process. Its mean, and this should look familiar, the mean of this Gaussian process is exactly the same, predictor that I gave you, that I showed earlier, that was the result of kernel methods. So this is, well, when we're talking, when the kernel is the kernel of the Gaussian process. So the posterior mean and the predictors of a Gaussian process and the predictors issued by a kernel method, by the corresponding kernel method, are actually the same. So that's the strong that's the strong connection between Gaussian process and kernel methods. So here I'm just stating this thing. So posterior mean of Gaussian process regression is the same as a kernel predictor. But unlike kernel methods, so what we have here, so posterior of a probability distribution. So the posterior is a probability distribution, and it provides to you confidence intervals. And these confidence intervals are based on the variance of the posterior kernel. So these confidence intervals at the point x are based on the variance of the Gaussian process, of the posterior Gaussian process at the point x. So we use these confidence, so that's exactly our approach. We use these Gaussian process confidence intervals in order to bound errors for kernel predictors. So more precisely, assume we have a target function f star in the RKHS. So this corresponds. So now we make assumptions precise. So this so the domain of our data is a d-dimensional unit sphere. So our results are just for the d-dimensional unit sphere. D can be anything, but it is for a sphere, and there is a strong reason why we need the sphere, because it's not clear how to understand the NTK outside of a sphere. Understand the spectrum of the kernel outside of a sphere. So here we restrict our data to the sphere and assume that the target function is in the corresponding RKHS. Moreover, assume, so we have an assumption on how we collect our training data. So we can also derive errors in the case that the training data is obtained randomly, but in our theorem we make an assumption, our theorem is valid for the specific case where the data collection is done in such a way as to minimize the confidence intervals. So basically to minimize the risks, to minimize the errors of the Gaussian process. So this is kind of active learning, if you'd like. So assume that the training data, so assume that the training data is selected so that each successive point is chosen so that to minimize the posterior variance of a GP, so after seeing the first k-1 data points. So how do we choose the data? Assume that I chosen already the first k-1 data points. Now, based on the training, based on these k-1 data points, I have a Gaussian process posterior, and I have confidence intervals, and I have variance at each point. Now, I will look at the posterior, and I will choose the next point for my data to be the point with the highest variance. So that's how we accumulate data. And we assume, so now we have a specific assumption on the neural network activation functions. So the activation functions of the neural network are ReLU activations to the power S. So basically, to the power 1 is the regular ReLU, but to higher powers, the activations will be more and more differentiable. And here is the theorem that we derive concerning the error bounds. So if f hat n is the predictor that trained on the data acquired in the way that I told you just now, on the data collected above, then with high probability, so with probability for every delta, with probability at least -1 minus delta, we will have that the difference between our target function, so here I'm missing a star, but fx is the target function, and our prediction is bounded by this expression here. So it doesn't matter what are the precise things of this expression, but I can precise numbers here, but I can just show you that you can see right away that the error bounds become worse as the dimension of the sphere goes to infinity, and the error bounds become better as the activation, as the differentiability of the activation functions become smoother. And these are uniform bounds for all x. I'm seeing I'm a bit over time. Do you have questions concerning that?
Hello?
Yeah.
I have a question. So you use Gaussian process bounds to derive error bounds for NTK. But it seems that this is not specific to NTK. It can be used in any kernel methods. Is that correct?
Definitely. This is correct. The methods,
okay.
So I do not have, well, I'll post, you can look at the paper, but I also post the next slides. I will not talk about them, but yeah, the idea of using a Gaussian process to derive bounds for the kernel is for kernel methods is absolutely not specific for the neural tangent kernel. This is for any kernel, but these explicit error bounds. So in general, the error bounds will be are a result of this thing. The posterior of Gaussian process has confidence interval. There is a strong connection between GP regression and the kernel predictor. And so from these confidence intervals, you will be able to derive kernel bounds for your kernel. But in order to derive explicit bounds, you will need to understand the kernel. And so these specific numbers that I'm depicting here are obviously, these are valid only for the specific NTK. But the idea is completely general.
Okay.
And
so
have been implemented before we implemented to NTK. Yeah. Okay.
So my question is, are there any other approaches to derive bounds for kernel methods, and why they may be good for traditional kernels but fail for NTK? So what's why Gaussian process is so special for NTK?
So I must say, okay, so the traditional method. So first of all, the traditional methods to derive bounds for NTK and methods depicted here instead in the end are not that different. Why they're not that different? Because, okay, so here we use a GP surrogate, but in the end, it boils down, so confidence interval for the GP depend on the variance of the GP, while the variance of the GP at the point X is given by the kernel of the GP at the point X. So to derive confidence bounds for the GP, you need to analyze the kernels. So you cannot escape from spectral analysis of the kernels, right? This will be so these two things. Will be prevalent in classic methods and in Gaussian process methods. But somehow we define. So this so Satar taught me at some point that the community is divided into basically was divided into two parts where people that are doing kernel methods and people that are doing Gaussian process. And there is actually a good paper online that connects and it's only a 2017, I think, paper that connects draws results from both methods and connects them between them. So there is a strong connection. So it basically takes the results for Gaussian process and applies them for kernels and vice versa. So, and this is only a 2017 paper, and it seems like these the results, the transferability of the results are not that well known. Of course, people know the the communities are a bit separated. So who's interested? Yeah, and so these methods are in some way similar to kernel methods, but the fact that you are using the GP surrogate, it allows you to sometimes it allows you to derive stronger bounds or different bounds in a bit of a different setting than to the classical kernel methods. But still, in the end, you will have to analyze the spectrum of the kernel. So this will be for both methods. Okay?
I see.
Yeah.
May I also comment on this?
Sure.
Yeah, I just want to say that the relation between GP and kernel ridge regression is pretty much the same as the relation between a linear regression model where we use a maximum likelihood estimate of the solution to a linear regression model using a regularized mean square error, which are the same thing, just two different perspectives, right? So one comes from a Bayesian perspective, one comes from the frequentist perspective, which is like a older divide in a statistic community in general. So, so the posterior variance is better well known within the GP community. While we can define the same quantity for the kernel ridge regression, but it doesn't have a natural or it doesn't have an intuitive interpretation. While in the GP community, it has an intuitive interpretation, so it's used more often. But what this theorem is concerned with, it is a frequentist theorem. So it's not like we're not assuming a prior for the objective function. So objective function is a fixed function in some specified space. It's not, the objective function itself is not a GP. We are just using that quantity to bound the error, which that quantity happens to be known in the literature as the posterior variance of the GP model, but it isn't.
Yeah, I know that,
Yeah, so by the way, what I'm saying here is that it's a good point. The probability here is actually on the noise. So we assume noisy data, but otherwise the target function is completely fixed.
Sure.
I just want my comment was about Professor Wang's question that are there other approaches for approximation in kernel. So there is another approach that is based on basically a scattered data function approximation theory, which is an older theory. Basically, if we have, let's say, a uniform set of observations from a function with a certain density, let's say we measure it based on field distance, like how far these points are from non-observed points, then what is the approximation error for that function? So I think alternatively, those kind of results can also be used for giving approximation errors. I haven't seen any work on that in the context of NTK or neural network, but I think it is better known in the context of GPs and again, like kernel methods. So basically, if you have a uniform data set over a given domain, what is approximation error for the other points of this function? There is a JMLR paper on that I can share in the chat.
Okay, great. So as Michael said, it's inevitable to do some control on the spectrum of this neural tangent kernel. So in all methods. So in this work, did you get a better characterization of that spectrum, or you just used old results or some existing results of the spectrum of NTK?
I'm not sure, Michael, if you're answering this question, if you want me to take it.
No, it's all right. I can answer. So, and you'll correct me if I'm wrong. So we do new analysis of the spectrum. So it hasn't been done for in the context of bigger power of values than S. So basically to show the dependence of on the smoothness of the function of the activation functions. So dependence of the errors as a type of smoothness of activation functions. And I'm also not sure that it has been done for more than a two layered network. I guess the spectrum itself, I guess there are results on the spectrum itself with value activations of a multiple layered network. But I think maybe Satar, you know better this, you will answer better this.
No, I completely agree. There's this ICLR 2020 paper that shows for ReLU networks, both deep and shallow networks have the same basically Eigen Decay, or if you just write the spectrum of the kernel, they characterize the decay rate of the eigenvalues, and they show that both shallow and deep networks have the same Eigen Decay. So I think the title of the paper is deep equals to shallow or something like that. I will share that paper as well. But what we prove in this paper, so basically part of our contribution is to generalize that result from ReLU to basically S times differentiable activation function. So ReLU is not differentiable, but if we have a activation function that is S time differentiable, that basically gives us a smoother model. Can we again characterize the Eigen Decay and prove some results for that? So basically we characterize the Eigen Decay for a smoother activation function. But our results show that here deep is different from shallow. So basically the implied constants in the rate of decay of the eigenvalues basically explode when the number of layers go to infinity.
Okay, that's very interesting. Okay, thank you for the answers. Yeah, I want to look at this paper for the spectral analysis for smoother values. Sounds very interesting. So it shows up in this error bar and shows the benefit of smoother ReLU activation.
Exactly.
Yeah. Thanks.
I have a question. So I'm wondering, in this bound, do you rely on the assumption that you have a prior on the parameters of the neural network to be like a following Gaussian distributions, each parameter to be ID Gaussian distributions and so on?
At initialization, yeah. So the NTK theorem is not the theorem. This convergence this convergence is true, or at least it's proved under the assumption of a normal Gaussian distribution. I suspect that other distributions can play a role, basically something that essential limit theorem would work for, but not everything. And specifically, if you initialize by something deterministic, then it completely fails.
Okay, I see. So my question is that I think this is a common criticism to the Bayesian approach, is that in Bayesian approach, we usually assume a prior, but that prior may not be true. Or how can we verify if that prior is true? I think that is a common criticism to Bayesian's approach. So here, of course, the result is very interesting. But I'm also wondering, because it is basically based on the assumption that all the parameters following like the ID and the Gaussian distributed. So if that seems to be just one prior distribution. I'm wondering if you change the distribution by a little bit and so on, does that change the guarantees significantly and so on? I'm just wondering, because there is another kind of which, like the PAC, which aims to give bounds that is irrelevant to any kinds of distributions. Yeah, so I'm just wondering if it is possible to like extend the guarantees to other distributions, to other priors.
So as far as I understand, there are two things here. There is the theorem, which is not connected to our paper, which depicts this overparameter. Basically, what I'm sharing now, this overparametrized regime, and this theorem assumes that the neural network is initialized with a Gaussian distribution, or like you say, the parameters have a Gaussian. There is a Gaussian prior assumption in this. So the limit. And then you get that in the limit you have a very specific. So in the overparameterized regime, which is the limit, you have a very specific. Kernel. Now, if you had a different prior, then possibly in the limit, if there was a limit, in the limit. So, for example, for a if you would initialize by something which is non-random, then this formula. So the formula for theta xy will drastically change, and it will be a completely different kernel. And then, so I do not know how different it will be, right? I haven't analyzed the cases, but it will be a different kernel. And then when the derivation of error bounds that we did are specifically for kernel, are for this particular kernel, and for other kernels, I mean, you'll have to, the methods will work, but you'll have to understand the eigenvalues of the subsequent kernel. So I do not know if that answers the question, but there are kind of two separate. There are two separate things here: error assumptions that do not assume any, error bounds that do not assume any prior. They just error bound for a particular kernel, which is NTK. And there is how this kernel actually appears in the whole context. And its appearance in the whole context, it can be, I mean, the whole paper, we could have said just given a kernel like that, here are the error bounds. But it's interesting also how this kernel, why in particular this kernel. So this kernel appears in the context of the Neural Tangent Kernel work, and you have the prior there. So there is a division, and the answer is specifically, I have not considered what be the limit for other types of distributions. And as I said, I think that normal here is it's not just normal. It can be other types of distributions, but you need something independent or close to independent and in the domain of attraction of a normal law. This is my suspicion, but I have to check the details.
Okay, thanks a lot. Thank you. Okay, sorry, did you mute yourself? I cannot hear your voice.
Yeah, I muted myself in case there are other questions I wanted to.
Yes, we may still have time for a couple questions. We can also take other questions offline, either to Slack or just get in touch by email.
Yeah, I just noticed that we have some new participants to this seminar. So yeah, I think most of them are students, and yeah, students are encouraged to ask questions. So yeah, maybe next time, if you have any questions, you can just unmute yourself and ask. Yeah. So we also advertise this seminar in our courses. So that's why there are some new students joining this seminar. And maybe at some point we can make this seminar physical in NTU. So yeah, I think we can discuss with Professor Wu and Professor Lee offline about this.
That sounds a good idea. Yeah, we can definitely discuss about it.
Yeah, because then I think students can get to know each other and discuss privately of the seminar. And that is a good way to interact.
Yes, thank you. That's great.
Hi, I'm Mark. About the this for this seminar physical, and we our MediaTek Research Taiwan has a room that can in Taida Xuexin can provide the room for you. Okay.
Yeah, Mark, thanks.
So maybe we can discuss this offline, and
yeah, okay.
I can forward an email to everyone with the informations of basically the location and how they can participate.
Yeah, I think Mark could take a lead to maybe schedule a new time for the physical seminar if we're going to run it physically.
Okay.
8 p.m. may be too late for many people. So
yes, sure.
Yeah,
we should do that.
Okay. Thanks a lot. I learned a lot today. Thank you.
Thank you very much. Thanks a lot. Thanks.
Okay, thanks everyone. Thanks, Michael. See you soon.
Okay.
See you
See
in
you.
2 weeks.
Okay. Bye-bye.
Bye-bye.
Bye-bye. Thank you.